Today we will talk about matrix representation of metabolic flux analysis solution. Last week we have written our differential equations. We made steady state assumption. We equated all those equations to zero, and then in the example we have covered in the class, degrees of freedom was 1. So we have 10 unknowns, 9 equations. We have specified one of the unknowns, glucose uptake rate, and we were able to predict the rates of all 9 unknowns. And we did this by writing all the equations one by one, and by manipulating these equations and trying to reduce the number of equations by replacing some of the unknowns with the equations obtained coming from other equations. There is a much easier approach by using matrix representation. So that's what we will cover today. And today I'll talk about carbon mole concept, which was popular in 90s, 80s. And I will also share with you some of the early examples of steady-state metabolic modeling from 70s and 90s. Let's start with the steady-state modeling with matrix representation. We have covered this example before. So here we have 4 metabolites within the system boundary. So our number of equations is 4. And we have 6 unknowns. So our degrees of freedom is 2. With the steady state approach, all the left-hand side will be 0, like this. And we need to solve this system of equation. By using the manual approach, we would say V1 is equal to V2, V4 is equal to V6, V3 is equal to V5, etc., etc. With the matrix representation, we can define all those equations in a matrix format, and by using a programming language environment, we can easily solve this set of equations. So I will talk about this matrix representation. We define a matrix, and the rows of this matrix represents equations. We have written an equation around metabolite A, right? So the first row in our matrix will represent this specific equation. Then we have written an equation around metabolite B. So this was our second equation, which means that the second row in our matrix will represent this second equation. Similarly, the third row will represent our third equation, and the fourth row will represent our fourth equation, which is the balance around metabolite D. This means that in this matrix, the rows will correspond to metabolites around which we have written a mass balance, and the columns will correspond to unknowns. In this specific example, we have 4 balances and we have 6 unknowns. So the dimension of our matrix will be 4 by 6. 4 rows, 6 columns. Let's see how we write each equation in matrix format. So this is our first equation. What do we see here? We see 1v1, right? There is 1 here, 1v1, and we have minus 1v2. So we write this information in the first row here. We have 1v1, we have minus 1v2. And in this first equation around metabolite A, we have 0v3, we have 0v4, we have 0v5, we have 0v6. So now we have represented the first equation around metabolite A in matrix format. The next step is to write equation 2 as the second row of our matrix. Do we have any V1 in second equation? No. So we should write 0 for column V1. We have a V2 in second equation, and its coefficient is +1. So we should write 1 as the second element in the second row of our matrix. We have V3 in our equation, so I will write -1 here. We have V4 in our equation, I will write -1 here, sorry. And we don't have any V5, we don't have any V6. So that's how I write second equation in my matrix. You see, this is the row. Similarly, I will write the third equation. So V3 will be 1 in the third equation, V5 will be -1, and the rest will be 0. And when it comes to the fourth equation, the equation around metabolite D, I will have +1 for V4, I will have -1 for V6, and there is no V1 in the last equation, no V2, no V3, no V5. And our matrix representation is ready now. And let me repeat, in this matrix representation, rows correspond to the equations around metabolites within the system boundary, right? Each row corresponds to those metabolites. And the columns, on the other hand, correspond to unknowns, right? Our unknowns are the rates of those reactions. So columns correspond to the reactions and their unknown rates. So we had this toy metabolic network, we had this set of equations, and we have represented the set of equations in matrix format here. This is our matrix, and this matrix is referred as stoichiometric matrix. So this set of equations can be written in matrix format as the multiplication of stoichiometric matrix, always designated as S, and its multiplication with unknown vector. There should be also V5 and V6 here. Sorry for the mistake. So because we have 6 unknowns, right? So we will have a vector here from V1 to V6. And then the right side, the other side of the equations will be a 4×1 vector with all zeros. The first equation is equal to 0, the second equation is equal to 0, the third equation is equal to 0, and the fourth equation is equal to 0. And this is always represented like this. S is our stoichiometric matrix, V is our unknown vector of rates, and 0 is due to equating mass balances to 0 in steady state assumption. So 0 here is a vector of zeros. So the dimensions of S matrix is usually referred as n by m. A stoichiometric matrix will have n rows and m columns, n by m. And n is number of rows due to mass balances around metabolites within the system boundary. So n is related to number of intracellular metabolites. And m columns, that's the number of columns. And columns represent reactions, right? Reaction rates. So m is the number of unknowns or number of fluxes. So if you write this S dot V equals 0, in this specific example, the dimension of S is 4×6. We have 4 balances, 4 mass balances, and we have 6 fluxes in this system, 4×6. And the dimension of V will be 6×1. We have 6 unknowns, 6 rates. So it's a vector of 6×1. And if you multiply a vector of a matrix of 4×6 with a vector of 6×1, you need to get a vector of 4×1. So the right hand side will include, in this specific example, a vector of 4 zeros. So S dot V equals 0 is the matrix representation of our steady state mass balance based modeling approach. There's one more thing I would like to emphasize regarding this matrix representation. Indeed, there are 2 alternatives to fill in the stoichiometric matrix. So far, I have talked about one of them. So what we did was to fill the stoichiometric matrix row-wise, right? First, we need to write mass balances around each metabolite. So we have our equations, and we filled each equation one by one, right? Equation 1 to the row 1, equation 2 to the row 2 of the matrix, etc. There is a much more practical column-wise approach. So the good thing regarding this approach is that you don't have to write mass balances. You don't have to write the equations. And in the column-wise approach, we fill each column, each reaction one by one, rather than filling the stoichiometric matrix row by row, we do it column by column. And we do it without writing the mass balances. We just use the coefficients of metabolites in the equations. I will show you now how. So for this toy system, this was the set of equations we had. We had uptake of A, we had secretion of C, secretion of D, and we had 3 intracellular internal reactions. So in the column-wise approach, as I said, we don't have to write mass balances. We can directly use this reaction list to construct the stoichiometric matrix. How? This is the stoichiometric matrix, empty. We need to fill it in. So first we will fill the first column. What we do is we look at the first reaction. There is no B in the first reaction, 0 for B. There is no C in the first reaction, and there is no D in the first reaction. There is A in the reaction, and A is a product. So we write +1 here. Plus means it's a product. Now reaction 2, second column. Again, we don't have any C, we don't have any D here. We have B as a product, +1. There is A, and A is a substrate. For substrates, we write -1. So the coefficient of the matrix, the coefficient of the reaction is used to fill the matrix with the corresponding numbers. And plus is used for the products, minus is used for the substrates. And if you do this, you will get exactly the same matrix given here. As you see, this is much more practical. You don't have to write those balances. You can just check the reactions, and at the end you will have your stoichiometric matrix ready. One thing, if your reaction, these reactions are simple, the coefficients are always 1. That's why our stoichiometric matrix looks binary. Only there are ones, -1s, and 0s. But of course, if, let's say, the fourth reaction is from 2B to 3D, then for the fourth reaction, you need to write for B -2 and for D +3. You use these coefficients always to write the corresponding column. So 2 and 3, these are the stoichiometries of the metabolites in the reactions. That's why this matrix is referred as stoichiometric matrix. In the column-wise representation, you use the stoichiometries of reactions to construct this matrix. So let's make an overview. Our focus is the steady state analysis, steady state metabolic modeling. So we will have this S dot V equals 0. All steady state metabolic modeling is based on this equation. And for some of the rates, we will have measured values, right? So this second one represents that. And by using this information, our goal is to predict reaction rates, to predict fluxes. This approach is very practical because you only need the reactions themselves, the stoichiometries of reactions, right? and you need some measured rates. For more advanced versions, we will talk about this later, the reversibility or irreversibility of reactions is also important. So this approach uses stoichiometric coefficients of reactions to construct a matrix of m by n. M is number of within boundary metabolites. It's also number of rows. You can also call it as number of equations. And n, on the other hand, is number of columns, number of unknowns, or number of reaction rates. So S matrix indeed is a representation of the metabolism of your organism in silico, in computer. We can group steady-state metabolic modeling into two. One is if your system is determined. And this version is usually referred in literature as metabolic flux analysis, MFA. So here, degrees of freedom is 0, or degrees of freedom is greater than 0, but you measured a set of fluxes equal to the degrees of freedom in number. So you make the system determined by using these measured values. And at the end you have a determined system. It is very easy to solve determined systems. You can use matrix inversion or Gauss-Jordan elimination. We will talk about this later. And the second approach is underdetermined systems. For metabolic network-based modeling, I have already shared with you the information that the number of reactions is usually higher than number of metabolites in metabolic networks. So metabolic networks are usually underdetermined, and degrees of freedom in metabolic networks is usually very high, especially if you are dealing with genome scale metabolic models. Degrees of freedom will be more than 100. So it's not that practical to measure 100 rates to specify them and to make the system determined. These underdetermined systems are solved by using optimization, and solution of underdetermined systems by using optimization for metabolic networks is referred in literature as flux balance analysis, FBA. Here, in the optimization problem, we maximize or minimize the values of one of the unknowns to choose one solution among many possible solutions. And the solution is usually possible by using linear programming or quadratic programming. So, how would we use matrix representation of sets of equations for determined systems to solve the unknown rates? We have this in hand, s dot v equals 0. This is the approach. The S matrix is grouped into, the columns of S matrix is grouped into two, S-calc and S-mes. So we have our stoichiometric matrix, right? Where have each column represents an unknown. Let's say you have measured V3 and V5 and you want to use this V3 and V5 as measured rates in your solution to make the system determined. Then you rearrange this stoichiometric matrix such that V5 and V3 are together in one part of the matrix and all the other columns are in the other part of the matrix. So this part of the matrix is referred as S measured, and this part of the matrix is referred as S calculated, to be calculated. You should do for solving unknowns for determined systems using matrix representation is to group the columns of S matrix into two different matrices. One is S matrix to be calculated. I mean, that refers to the rates that will be calculated, and S measured is the part of the stoichiometric matrix which includes the columns of the reactions, the columns that correspond to reactions that will be used as measured in the solution. Remember how we define S matrix, as always M by N, and N is greater than M most of the time. Number of reactions is more than number of metabolites within the system boundary. So this means that to make the system determined, you need to measure M by N times fluxes. So if M is 8, you have 8 equations, and if N is 11, you have 11 reactions. This means that degrees of freedom is 3. You need to measure M by N fluxes, in this case 3 fluxes, to make the system determined. So you group original S matrix, stoichiometric matrix, into two different matrices. So this means that this vector of rates will also be categorized into two: the rates that are measured, the rates to be calculated. And this representation you can write also like this. So by separating the two matrices. So to be calculated part, the measured part. Here the interesting thing is, to make the system determined, we will measure M minus N flux. So S measured matrix will have M minus N columns. S matrix had N columns. Now, since M minus N of the columns of S is in S measured matrix, S to be calculated matrix will have N columns. M plus N minus M. So this will be not M minus M, but N minus M. So if you sum up M plus N minus M, this is the number of columns in S calc. This is the number of columns in S measured. So the summation will give you N, right? The total number of columns in matrix S. So my point is, by making this grouping of the columns in S matrix, you will get a calc matrix in square format. It already has m rows. Now it will have m columns. This is important. You will see why in a minute. So we have this equation, and our goal is to calculate this, right? VCalc, because we already know the stoichiometric matrix from reaction coefficients, and we already measured some rates. So the only unknown in this equation is this part. So I can send this part to the other side of the equation, like this, right? Then I can multiply both sides with the inverse of S-calc matrix. Then I will get rid of S-calc on the left-hand side, and I will get an expression for VCalc. So if I know my Vmass vector, if I know this S measured and S to be calculated matrices, I can use this formula to calculate my unknown rates. So all you need to do is to construct stoichiometric matrix, then group the stoichiometric matrix into two, represent those in matrix or vector format, and put them into this equation. And when you multiply them by using R, MATLAB, or the any environment that you have, you will get a vector of the values of the unknown rates in vector format. So I emphasized that this S-calc matrix is a square matrix, m by m. We can take the inverse of only square matrices. So that's why it is important. If you don't have a square matrix for S-calc, then you cannot use this expression. But since we specify always rates equal in number to degrees of freedom, we will always get a square matrix of S-calc. But there may be other problems. I will shortly talk about those problems now. A square matrix, so in order to take the inverse, a matrix has to be square. But it is not enough to take the inversion. A square matrix is only invertible if it doesn't have any dependent rows, if it doesn't include any dependent equations. I will talk more about this. Last week we have already talked about dependent, independent equations when we defined degrees of freedom. Usually, if in a reaction there is NADH in one side, there will be NAD on the other side. So NAD and NADH, they are always coupled, almost always coupled in the reactions. The same with NADP, NADPH, most of the time the same for ATP, ADP. So what does this mean? If you write a balance around NADH, or if you write a balance around NAD, since they always take place in the same reactions, when you write those balances, you will get the same equations. So writing a balance for both NADH and NAD at the same time will introduce dependent equations to your list of equations. The same with NADP, NADPH, the same with ATP, ADP. So, in this case, if you have dependent equations, in order to apply this approach, first you need to remove some of these dependent rows from your set of equations. Otherwise, you would get a square matrix, but you cannot take its inversion because it has dependent rows. For the examples we cover now, like 9 unknowns, 10 unknowns, 20 unknowns, etc., we don't have this problem. So we can easily apply this without checking the dependency. But you should be careful not to write separate balances for both NADP, NADPH, or NAD, NADH, or ATP, ATP for a given reaction list. If the reaction list has a manageable number of reactions, let's say 20, you can easily check by eye if there is an NADPH in a reaction, there is always NADP on the other side of the reaction. If this is the case, this is always the case, then this means NADP balance and NADPH balance will be dependent. So you need to write a balance only around one of them. Then you will get rid of this dependency problem. There's a very quick way to check if there's any dependent row in your matrix S or S-calc, checking the rank of the matrix. In MATLAB, for example, you can easily check this by using rank A function. A is the matrix. If the rank of your matrix is equal to number of rows of your matrix, this means that your matrix is in full rank and there is no independent equation. So this is good. But if the calculated rank of your matrix is smaller than the number of rows of your matrix, then this means you have dependent rows in your S matrix or in your S-calc matrix. So in this case, you need to take an action. You need to check and you need to remove the dependent rows from your matrix for determined systems. Let me repeat. These are all specific for determined systems. For underdetermined systems, we have a different approach. There is an approach to identify dependent rows in your matrix. What you can do is you can write a for loop, and in this for loop you can remove each row in your matrix one by one, and each time you remove a row you can calculate the rank of the matrix. If the rank of the matrix doesn't change when you remove a row, this means that row is a dependent row. Let me repeat. If you remove a row from your matrix, and when you calculate the rank of the matrix, you still get the same number you had calculated before removal of this row, this means that that removed row is a dependent row. So this is one approach to identify dependent rows in your matrix if your approach is MFA, solving the unknowns by using determined systems approach. So you should always pay attention, you should always keep in mind that if matrix is not in full rank, you cannot take inverse of the matrix, so you will not be able to apply this formula here.